Hello, geodesy lover. A few notes on Transverse Mercator. Now, we previously talked about Mercator projection. We mentioned that it is a cylinder that is normal to the Earth, meaning the axis of the cylinder coincides with the rotation axis of the Earth. The cylinder is tangent to the equator. That's how it was originally designed. Later on, and here we are talking about 2 centuries after Mercator, a geodesist called Lambert designed a projection satisfying conformality, and he built that analytically, like Mercator itself. It is an analytical map projection, even though Mercator, when he developed his system, he referred to a new arrangement of parallels and meridians. Lambert made a full development of a system that is called the Transverse Mercator. And it's transverse because the cylinder now is perpendicular to the rotation axis. So the cylinder is transverse. It is tangent to the Earth. It is tangent to the Earth along a meridian, and this meridian is called in many different ways. It's called the central meridian, the standard meridian, or the reference meridian. So this is what we have here. This is the Earth. This is Mercator. This is Transverse Mercator. Now it is tangent along a meridian. So this meridian, called the central meridian or the standard meridian or reference meridian, is represented as a straight line in the projection. It is projected as a straight line. And all other meridians are projected as curved lines facing the central meridian. So this is the central meridian. Here's how the meridians look like. Okay. Equator is represented as a straight line. So this is the equator. And all other parallels are curved lines, curved towards the poles. Okay. So here is my nice diagram of the transverse Mercator, and here we have the projected. This is the reference meridian. This is, in this case here, equator, and we have meridians, and we have the parallels. Okay. Mapping equations of this projection is not written directly. They must be built step by step, and their derivation is very involving. So we are just going to make a reference to how the starting point. We are going to have the longitude represented in real space, and the isometric latitude represented in the complex space. On the mapping plane, we have now the grid component X as in the real space. Here we have the complex Y and of course they are a function of this quantity z. The development is evolving. The resulting mapping equations from the development is as follows. And it is interesting to have a look because it is very intuitive, at least the understanding of it. Here we have the x and the y grid equations as a function of latitude for the x, as a function of the difference in longitude for the x, function of latitude, function of difference of longitude. What is this difference of longitude? This delta lambda refers to the reference meridian. So it is basically delta lambda is going to be the longitude of the point minus the longitude of this reference meridian or the central meridian or the standard meridian. Now, if you look at these two equations, what we can see here first is this term n, so every term here is multiplied by n. Okay, so the first term is n cosine phi delta lambda. We have seen this expression before. This expression of a arc of parallel. And then we have all the rest as a correction for that. For the y component, this is the expression m delta phi. We have seen that also. This is the arc, an arc of meridian. And then we have all the other terms that are correction for that. So x and y, what we have here, this is the central meridian. This is equator. Let's think of on the first quadrant. This is meridian. This is the parallel. So let's consider we have a point here. Okay, this is equator. My dog is someone stepped on its tail probably. So this is y and x, y-axis. This is the y component. This is the z, the y. This is the x component. Okay, so what we have in here essentially, let me use a different color. This quantity here is the arc of meridian. So can we evaluate as the integral from latitude 0 to the latitude of the point, m d phi. So this is this guy here. Okay. And now we have this guy here, which is what? It is n cosine phi delta lambda. Okay? So all the other terms, they represent terms that will essentially take these quantities and have them represented along the grid, the grid system. The inverse mapping equations, that's not as intuitive to look at. We have the delta lambda. Again, we're computing, if you know delta lambda, we know that delta lambda equals to lambda p minus lambda 0. We know lambda 0, so lambda p is going to be delta lambda plus lambda 0. Okay. N is the radius of curvature of the meridian section. Of the prime vertical section. Oh, we have this phi prime here. What the heck is that? We also, for latitude, we have the latitude expressed as a function of this phi prime. Phi prime is called the foot point latitude. Let us have a look at it. So, what the heck is this foot point latitude? Let's realize that the situation we have is we know the grid coordinates. We want to determine the latitude of point, longitude of this point P here. Okay, x p, y p, phi p, lambda p. We know this is y. We know this is x, right? We want phi lambda. So here is the longitude, okay? Lambda of the point P, latitude of point P. Now, the interesting thing is that in a grid coordinate, we know the latitude of this point here. This latitude, okay, that's what we call foot point latitude, because it is the projection, well, like the projection along the y, okay, points of same y value. It hits here. We know this latitude of this point here. This is phi prime. But what we want the latitude of this guy here. So the whole computation now is going to be computing like a correction for this segment here. Okay, so this is the meaning of the foot point latitude. Gamma and scale factor. Gamma is given by this expression. The important thing here is that if we use the correct value of delta lambda and the correct sign of delta lambda and the correct sign of latitude, we will get the meridian convergence with the sign ready to be applied in the equations for the angular reduction. So again, the meridian convergence is a function of latitude and difference of longitude from the point of interest to the central meridian. The scale factor, given here two expressions. One expression is as a function of geodetic coordinates. Okay, it's we have these symbol here, approximation, because we could have actually write something like that. This is a truncation, the same as here, but I put the the three little pigs here. Here, three little pigs, three little dots. And anyway, the first one is a function of the geodetic coordinates. The second is a function of the Cartesian coordinates, in this case x, and the foot point latitude. Now, one interesting thing is that this expression here, okay, if you want to make a fast computation of the meridian convergence, we can use this term here, delta lambda sine 2 phi. It's a very good approximation. In geodetic computations, we're going to use something slightly more accurate. For the scale factor, we can also use this term here for a quick evaluation. Okay, but anyway, what we are seeing here are the expressions for this transverse Mercator, okay, and go from transverse Mercator to universal transverse Mercator. We are just a click away. It's just a detail. T minus T correction. Here we have an expression as a function of the grid coordinates. N is the prime vertical radius of curvature. And the S minus L correction, this is this distance between the distance on the mapping plane. This is the grid distance. It is insignificant, okay? It is basically 0, okay? Particularly when we consider delta lambda varying between -3 and +3, which is basically what we use in practice. UTM, for example, does that. So just so that you understand, we are not saying this here indicates the definition of a scale factor, distance on the mapping plane, distance on the reference ellipsoid. This guy here, okay, L coinciding L, okay? This is the projected, this is the distance on the ellipsoid, this is the distance that we use in the computations, okay, in such a way that S, this X here, equals to K SE when we do the linear transformation. So these expressions, the whole idea behind this discussion on transverse Mercator is that we have look at how the projected meridians and projected parallels, they behave. We have looked at the interpretation of the mapping equations, okay, when we go from geodetic to grid, and we look at we have these the arc of meridian, the arc of parallel, plus additional terms. When we go from the grid to the geodetic coordinates, we have to do that using the footprint latitude, and we have presented these general expressions for meridian convergence, for the scale factor, for T, and for the T minus T correction and S minus L correction, which, as I mentioned before, for in the for all the coordinate system, the map projections that we use in geodetic computations, it is 0. Okay, 0. In essence, the only linear transformation is this one here for the distance. Okie dokie. So next step, UTM.